Hey, Carly.
Hey, Waf.
Now let's look at doing correlation inside of Python. And let's do this through our classic data set we're looking at, which is the Diamond data set. So this data set is a classic data set that's been around for decades that are used by almost every data scientist. So we feel like it's important for you to see some of these classic data sets as well. This data set contains over 50,000 diamonds and has characteristics like the price and the carat weight of the diamond. These are two really important factors. These diamonds range all the way from $300 for just the gemstone to multiple thousands of dollars. And the carat weight ranges from 0.2 carats all the way to 5 carats. And for diamond weights, a 5-carat diamond is a huge diamond.
Yeah.
I think I've never seen one. Have you seen one?
No, I don't think so.
So yeah, everywhere from a small diamond to a massive diamond. And then stuff like the cut of the diamond, the color, the clarity, X, Y, and Z dimensions, depth, and table. Let's go ahead and explore this data by downloading it. I've uploaded it to my faculty website so that it's easy for us to download in a CSV file. So to grab it inside Pandas, since we haven't done this in a while, this is just going to be import pandas as PD, and then it's going to be df is equal to pd.read_CSV, and we'll open parentheses, and inside of quotes, I'm going to type https://waf.cs.illinois.edu/discovery/diamonds.csv. And then I'm going to type just df at the bottom of that cell to print out what's in the diamonds data set.
And it looks like this is a data set with 53,940 rows and 10 columns.
So over 50,000 diamonds. And let's just go ahead and do some exploratory data analysis by creating a scatter plot of the carat weight versus the price. So if you do df.plot.scatter, and inside the parentheses do x equals the column name of the carats, which is just carat all lowercase, and y is equal to the column name for the price, which is just price all lowercase as well. And this is 50,000 or almost 54,000 data points, so it may take a second to run. And once it runs, we should see a scatter plot that looks just like this.
OK, here it is running really quickly, and that is exactly what I see.
Awesome. So a couple of different puzzles. What is mapped to the x-axis of the scatter plot? Well, here the carat weight is on the x-axis. And what do we call the x-axis, Carly? Is this dependent or independent?
So this is the independent variable.
So I'm going to write this independent. Oops. Independent. And then what data is mapped to the y-axis of the scatter plot? So here, the y-axis, you can see the label is price, and this is dependent. And then the third color is, what is the color value of the diamonds displayed on the scatter plot? So do we map the color, which we saw up here? The color is going to be all the way from D being the best color in this data set to J being the worst color. Is the color of the diamond represented in the scatter plot?
It looks like no, it's just the price and the carat.
Nope. So that is information that's in our data set that's not in this plot. So we can use color, it's in the data set, but we chose not to represent it inside of our plot. So even though there may be additional data in the data set, the scatter plot's only going to plot the data that we ask it to plot. So let's go ahead and look at correlation coefficients. So we've already loaded our data frame in from the website on the first part of this. And there's a beautiful command that's super simple that's going to give us the correlation between every single column's value by just running df.core and then open and closing parentheses.
And this actually gives me a table or a kind of a matrix looking object.
Yeah, two-dimensional table. And all the column names and all the row names are actually the same.
Yes.
So we have this, what we call a correlation coefficient matrix. This is a matrix of every possible combination of correlations between all of the variables in the data set. But there's a few variables we don't see.
Ooh, yeah. I actually don't see the color variable that you mentioned.
Exactly. So there's no color variables, and that's because the color variable wasn't a numeric variable. So the color variable was D through J.
That makes sense because you need numbers to calculate the correlation coefficient.
Exactly. So this shows the correlation between all numeric columns. And we don't have a way to create a correlation between a numeric column and a non-numeric column. So there's a number of observations. So the first one is this table has a special name, and we call this the correlation matrix. And in this matrix, the second question is, what is special about the main diagonal of the matrix? So the main diagonal of a matrix is always the diagonal that runs from the top left to the bottom right. And that's called the main diagonal of any matrix. And this main diagonal is always 1. That is a perfect correlation. Why would that happen, Carly?
Yeah, so it looks like if I'm just looking at the first one in the upper left-hand corner, it looks like that's the correlation between caret and caret. So
Yeah.
between basically the values and itself. So that makes sense that it would be a perfect correlation because if we know the caret, we know the caret.
Yeah, so it's saying that, can we predict the price of the diamond by being given the price of the diamond?
Yeah. Yep,
So,
we can.
yeah, if I told Carly this diamond was $24,000, she could tell you the diamond was $24,000, and that'd be a perfect match. So the main diagonal of the matrix is always a self-correlation and is always 1.0. And that's a good check to make sure we're actually doing proper correlation, because if I give Carly a price and then Carly can predict a price perfectly, then that's a perfect correlation.
We are good.
What does a correlation of 1.0 mean? It means it's a perfect prediction. So the fourth observation is, what is always true about the upper triangular region and the lower triangular region of the matrix? So the upper triangle region of the matrix is going to be everything on the top right of the main diagonal, and the bottom triangle is going to be the lower triangle is going to be everything below the main diagonal. And if we look, I see that on the top, I see 0.03 in the top corner and then 0.03. Then as I go across, I see 0.18, 0.18, 0.92, 0.92, 0.98, 0.98. So the upper triangle region and the lower triangular region is always a reflection. The regions are always a reflection of themselves. And what this means is a correlation between two variables. It does not matter which order we look at. So the correlation between the carat weight and the depth of the diamond is the same as the correlation between the depth of the diamond and the carat weight. So it doesn't matter which way we state the correlation, that we can swap the order and it still means the exact same thing. The correlation matrix, or the correlation value, does not change. The fifth question is, the correlation between the carat weight and the price is blank. What does this tell us? So I'm going to go over and look at the carat weight and the price. So Carly, I see the correlation between the carat weight and the price is 0.92.
Yeah, I see the exact same thing.
So what does 0.92 mean here?
So in that case, 0.92 is pretty close to 1. It's a strong positive correlation, and it means in the context of this problem that as the weight increases, so does the price, which in terms of diamonds makes pretty good sense.
Yeah, so what does this tell us? There's a strong positive relationship.
Yes.
So as the carat weight goes up, we expect the price to go up as well, and we expect it to be a pretty strong relationship between the two of these. All right, the correlation between the table and the depth of the diamond is what? So I'm going to go ahead and go for I see the table column and the depth column. I see negative 0.26.
Same.
So the correlation between these two is negative 0.26. And Carly, what does the negative 0.26 tell us?
So that tells us that there's a negative correlation, meaning as one of the variables goes up, the other one goes down. So as the table goes up, the depth of the diamond actually goes down.
But the value is just 0.26. Would you consider that strong or pretty weak?
I'd consider that pretty weak.
Yeah, so I'm going to say there's a weak inverse relationship that as one goes up, the other goes down. So as the table goes up, the depth is going to go down. So we see that there's a weak inverted relationship here, that There may be some diamonds where the table might go up a lot and the depth may only go down a little bit. So the relationship isn't very strong, but we know there's a slight relationship that as the table goes up, the depth goes down. And we say that's an inverse relationship.
Yes.
That as one goes up, the other goes down. They go different from each other. And the last observation, the correlation between depth and price is what? So if I go to depth and I go to price, I see negative 0.01.
Same.
So negative 0.01, that is almost zero. What does that tell us?
Yeah, so that tells us there's not really a relationship between these two variables, that price and depth, there's hardly any linear relationship between them.
Yeah, so I'm going to say no relationship. So as the depth goes up, the price goes both directions, basically.
Right, we're not sure.
We can't make any prediction based on the depth going up or down. If you give me the depth, if I say, Carly, this diamond has a depth of 10 millimeters, you can't give me any reliable information about the price of that diamond.
Exactly.
That there's no predictability between the depth and the price of the diamond because the correlation coefficient is 0.01, a really, really tiny value, really close to zero. So that is the beginning of how correlation coefficients really begin to play into how a computer can predict information about data. These correlation coefficients give us the predictive power of a linear regression model. Because if we're able to curve the line or do different things with the line, we may be able to predict the data with that information. But for just a linear regression model, this gives us the strength of the model by simply looking at the correlation coefficient.